We're looking at the comparison test here. Let me give you some quick slogans to motivate the way we want to think about the comparison test, and I'll state it. I'm not going to prove it real carefully, but I'll talk about briefly why it's true, and then we'll get to examples. So slogans, our big slogan is a series that is an infinite sum of terms converges, generally, roughly speaking, when its terms, the individual sequence of terms, goes to 0 fast enough. And that's a little vague, and we have, of course, making it precise is why we have to do all this work of these tests. And two more slogans that are very specific about comparison. One is that better than good is good. So if you have something that you know, some sort of simple reference standard, and you know it's good, in our world that's convergent, and you can show that the more complicated series you're staring at that you'd like to analyze is better than that, it's also going to be good, in other words, convergent. And the flip side of that is worse than bad is bad. If your reference series diverges, and you know you can show that your more interesting series is worse than that, in the sense of its terms don't go to 0 as fast, then it's also going to diverge. In particular, there's no slogan that says better than bad is something definite. We just don't, that doesn't say anything. Or worse than good. Could be good, could be bad. And so we're going to have to pick our reference comparison based on whether we think we're trying to show something is convergent, good, or bad, divergent. So let me talk briefly about the applicability before I state the precise the comparison test. The applicability here is to a series with non-negative terms. So we've got some sort of summation. This doesn't have to start with 1, but let's just say 1 for now. That's the kind of series we're talking about, and its individual terms should be non-negative. Roughly, that's because we're doing size comparisons here. All these comparisons are based on size, and the signs are just going to get confusing. Another way to say it is that there's really two different ways. If we look at this partial sums of a series, what does it mean to say that the individual terms of a series are positive? It says something very special about, let's put K here. So let's do what we usually do. To carefully analyze the series, we look at the sequence of partial sums, the running totals. If you're adding up more and more and more positive numbers or non-negative numbers, then as the total number of numbers you add increases, you're going to get an increasing sequence of partial sums. So I'm not saying the terms are increasing. They're just known to be non-negative. But the partial sums is increasing. That sequence is increasing. Partial sums. And the important thing there is that it can't diverge by wiggling. In general, a sequence can converge either because it blows up, or it can converge by wiggling and never settling down. If you have some increasing sequence of numbers, then it's not wiggling at all. It's going in one direction. The worst it can do is maybe blow up to infinity. And if we know that these things are small in some sense, and that's what the comparison test is going to tell us, we can show that they're going to be capped and forced into a limit. Now, there's some deep stuff there about the fact that if you don't diverge by wiggling and you don't go off to infinity, you must converge to something. Some very deep stuff about the real numbers, but that's the slogan version anyway. If you have a sequence of the terms are non-negative, then the sequence of partial sums can't wiggle. It's monotonic, to be a little more precise, and it can only diverge in the most brute force way that it's just not, the terms are not going to 0 fast enough. So it makes the slogans I started with more accurate. So here's the comparison test. I'm going to state it with both good, better than good is good, and worse than bad is bad. So we have A sub n is a sequence of positive terms, and B sub n is a sequence of positive terms. And A sub n you want to think of as an interesting, complicated series, the terms of an interesting, complicated series that you want to analyze. And B sub n is going to be some simple reference series that you already know what it does, in particular whether it converges or diverges. Okay, so if A sub n is better than B sub n, so if you're positive and you're less, that means you're smaller. And I'm gonna leave a space for a little bit of a leave room for some wiggle room here. It's going to be important. And the sum of B sub n converges. And this is to infinity, but it can be n equals whatever. This is not particularly, the starting point is not important, and so we're just going to do an undecorated sigma to just be, say it's an infinite sum. Then the sum of A sub n converges. So if everything's positive, so the size comparisons are straightforward, and there's no wiggling, and you are better than this reference series and its sum converges, then your more interesting sum converges. And we would want to put something about, is this true for just one n or a few or all? All is the idea, but really eventually this should be true for all n. And so we're going to say for all n greater than or equal to some n. So the big N is some fixed number. So this, you would just say this, eventually my terms are smaller than the reference terms. This is a super common thing. A few terms, the first few 2, 3, 4, 100, a billion, don't affect convergence. They could radically affect what the sum actually adds up to, but they don't affect whether it converges or not. So this just gives you a pass, and we'll see how this works, that maybe the first few, the comparison doesn't actually work. You don't actually start out smaller than your simple reference, but eventually it does. Okay, and I do want to get to an example here, but it takes a little while to lay it out. We're almost done. If A sub n is worse than B sub n, for all n greater than or equal to some fixed n, and that guy's bad, then the sum of A sub n also diverges. So better than good is good, worse than bad is bad. So, there's nothing sacred about A's and B's, but we're going to use that terminology if we need to refer to various, the complicated series we're trying to analyze and the reference. So part of the trick here is finding the reference. If you're just given a series, people won't hand you necessarily what is the reference series to compare to. And part of it is knowing whether to try to compare it to a good one or a bad one. So the first thing to do is not actually hit it straight with the comparison test, because you need to invent that. You need to decide what the comparison series is. So the first thing to do is to be a little looser and say that, okay, 2 over 3k squared plus 5, when k is really big, let me just say, is approximately, you know what, that 5 is not going to be very important. When k is big, and this is the name of the game, what happens as k goes to infinity? Let's look at, oh, and I tend to like k better. I was writing it with n's because the book writes with n's, but I like k as a dummy variable better. Okay, that's approximately that. Well, the basic thing here is that it's a constant multiple of 1 over k squared. So this is very similar to the reason we've always had for limits at infinity. The top order, the highest degree term in any kind of polynomial expression dominates. And then constants only affect against the actual answer for the sum, not whether it converges or not. So basically this is like 1 over k squared. That's the first step you want to do, is isolate roughly what is this behaving like as it goes to infinity. So we would like to show that this is better than 1 over k squared. Oh, and what does 1 over k squared do? So this is a huge thing using the comparison test, is you need to have some stock of examples where you actually know the answer. Well, we know that the sum k equals 1 to infinity of 1 over k to the p converges, often people know this from the integral test. That's how we know it. There's other ways to do it. That's exactly when p is greater than 1, strictly greater than 1. So when k1 over k squared, the sum of that is going to converge. So we're going to guess this is good, and we want to show this is better than this known good sequence, this good summation, the series. And so let's do that. Now, one thing is the 2 up here does make these numbers bigger than if the 2 weren't there. And so certainly, like 2 over k squared is strictly speaking bigger than 1 over k squared. But again, that doesn't really matter in terms of how it goes to 0. It's just an overall constant factor. So the easiest thing to do is just say, look, that's 2 times. We know that we can multiply a series by a constant or divide it by a constant and not affect convergence. Okay, so we really just want to analyze this guy. Okay, now this is easy. We know that 3k squared plus 5 clearly is bigger than k squared. And so notice I'm starting out with a simpler expression that doesn't have the fraction in it, but where I can just start out with an inequality that I'm absolutely sure of. So start with something you're sure of. Then, when I take the reciprocal of that, it flips the sense of that inequality. Aha. So this is what we would call b sub k, and this would call a sub k here. You never actually have to trot out those terms, really, but in the nomenclature of how I wrote the theorem, this is how it would look. Here's your reference sequence of terms. Here's your interesting sequence of terms. And the comparison note, the inequalities happen on the level of the terms. I'm not writing summation is less than summation or summation is greater than summation. It's the individual terms of the new guy are less than the old guy. And, let's see if you can read that, yep. And the sum of 1 over k squared converges, because that's a known fact. So the sum, and I'll write it out a little carefully, of 1 over 3k squared plus 5 also converges. And so does this one, because it's just twice that. So that's a simple example of using the comparison test, and we'll make it a little more subtle in the next couple videos.